All right, let's get started. Where did I put my chalk? Okay, so last time we finished up logic. We did propositional and predicate logic, right? Rings bells. And so today we're going to be starting set theory. And you'll notice that we'll be using logic now in our definitions from here on out to define sets. To give you a little bit idea of the overall structure here, logic is pretty foundational. Here's logic. And then using logic, we're able to construct set theory. And then with set theory, we use set theory to define any other field of mathematics. Every field of mathematics ultimately reduces to set theory. Whatever field you're building up, you're ultimately constructing that field from sets. Computation theory is no different. So everything that we're going to be working with is technically a set of some sort. And so set theory is very foundational. It's the most foundational field there is after logic. Logic is more foundational than set theory because you can use logic also in fields that don't build up in set theory, like philosophy. You can still use logic in philosophy, we don't necessarily use set theory in philosophy. Okay, so set theory is what we'll be focused on today with set theory. Next question is, what's a set? For those of you who are comfortable with axioms giving you undefined terms, and then undefined terms get their meaning through the axioms, a set is an undefined term. For those of you where that doesn't make sense, you'll be fine with this intuition right here. What's a set? It is an unordered, unique collection. A set is an unordered, unique collection. What do we mean by that? Well, first off, some notation. So when I'm writing a set of objects, what do? I start by a curly brace. Then I write the objects that are supposed to be in my set, separated by commas. And then end curly brace signifies the end of the set. So here I've written out a set. There's 3 objects in there. The objects in the set are 1, 2, and square. There's a set of 3 objects. Here's another set. 1, 2, 2, square. Good? Now, when we say that a set is an unordered, unique collection, that unique part means that repeating elements in a set do not matter. Oh. So this set is identical to this set. Adding that extra 2 doesn't change the set. And we said unordered collection, meaning this set is identical to this set. We just wrote the terms in a different order. Order doesn't matter in a set. Repeating elements doesn't matter in a set. A set, intuitively speaking, is an unordered, unique collection. Good? Okay, so now we have some basic notation for sets. And we've probably already been using this, I don't know, but let's list it. So x, and then we have that backwards E looking thing, A. That means x is an element of A, or x is a member of A. A here is always understood to be a set, and we're saying x is something inside that set, A. For example, here's a set containing the numbers 1, 2, and 3. 2 is an element of that set. 2 is one of the things listed in this set. It's right there, since it's right there, one of the things in the set. 2 in the set is a true statement, or true proposition. Notice that x in A is a predicate, 2 in this set is a proposition. Make sense? Okay. Similarly, here's another set. What's in this set? This set contains 1, it contains the set containing 2, and it contains the set containing 3. The set containing 2 is a member of the set. It's one of the 3 objects that we listed in there. Our next notation. We have x in A, but now on that in symbol we put a line through it. That just means x is not in A. X is not an element of A. So, rewriting this set right here, here we have the set containing 1, 2, and 3. The set containing 2 is not an element of that set. 1 is an element, 2 is an element, 3 is an element. The set containing 2 is not one of the things in there. Similarly, 2 is not an element of this set. 1 is in here, the set containing 2 is in here, and the set containing 3 is in here. But 2 is not one of these elements. Make sense? And there's a lot of confusion between, that's often a point of confusion for a lot of students, is they see something like this and they say, oh, 2's in there. No, the set containing 2 is in there. The set containing 2 is a different object than 2 by itself. Make sense? Okay. Common sets that we talk about all the time, and you've probably seen a bunch of this notation already. That symbol right there, a circle with a line through it, that stands for the empty set. What is that explicitly? That is this set. This is shorthand for that, a set with nothing in it. N here, we use as a set of all natural numbers. I don't know if this author, you're fine. Unfortunately, there's ambiguity anytime we talk about the natural numbers as to what exactly that set references, and it varies from author to author. So it is either the set containing 0, 1, 2, 3, counting up like that, or it's a set without the 0 in there. Some authors mean it to include the 0, some authors mean it not to include the 0. I'm not sure which this author intends.
That's confusing.
It's very annoying that there isn't consistent behavior there.
Isn't there supposed to be some type of global...
It's just notation, and you don't get to dictate how other people use their notation.
No way. Even in mathematics?
Even in mathematics, some people use symbols slightly differently. Because one people refuse to use it one way, and one people refuse to use it the other way. So when you see the natural numbers, it's either 0, 1, 2, 3, or it is 1, 2, 3, etc. Which it is, depends on the author. For this class, I'll always mean it to mean 0, 1, 2, 3, and if I ever mean it to be otherwise, I'll explicitly say so. I always like to include the 0 case. Seems more natural to me. Anyway, so that's the natural numbers. Okay, what about the integers? So this is supposed to be the set of all integers. What is that? That is ... -3, -2, -1, 0, 1, 2, ... going on forever. And we'll also use this ... notation. That ... notation means you should be able to infer the pattern and extend it to infinity. So when you see that weird looking Z, that's shorthand for the set of all integers, which is an infinite set.
So it doesn't necessarily mean infinity, it means the pattern.
It means follow that pattern to infinity.
So it could be...
So if you follow this pattern forever, you'll eventually write the number 10,562.
I guess
so that's in there.
If there was only odds, would you follow the pattern of the only...
Yes. Whenever you see that 3 dot notation,
okay,
it says whatever the obvious pattern is, continue with it.
Okay.
And you'll notice that that's kind of inexact, and so we'll show a way that we can get around having to do that. This Q with the line through it, that is the set of rational numbers. What are the rationals? They're any fraction of integers. So basically any fraction you can think of. So 3/2 would be in there, -15 over 91 would be in there, etc. Any fraction of integers is a rational. Good? And then finally, that R there stands for the real numbers. If you don't know what a complex number is, then the real numbers are basically what you think of when you just think about numbers in general. Any number you think of, chances are you're thinking of a real number. If you do know what the complex numbers are, then you already know what the real numbers are.
So what's the difference between the Q and the R?
The Q and the R, pi is a real number. Pi is not irrational.
Right.
You cannot express a number pi as a fraction of 2 integers.
Right, I remember now.
Square root of 2 is also another common example. Square root of 2 is real. Square root of 2 is not rational. It's irrational. So the rationals together with all the irrationals gives you what we call the real numbers. Okay, any question on those basic sets? No.
Okay, just practice.
You can remember that that's the naturals, that's the reals, and how you're supposed to remember that that's the integers and that's the rationals. The reals was already taken, and so we needed something for the rationals. And since they come before the reals, well, Q comes before R, so why not? Z, who knows? I have no... It's like an I tipped sideways. I don't know. Anyways, so those are common sets. So now if you were to see something like x in n, this is shorthand for saying x is a natural number. Or if you were to see y not in z, that's shorthand for y is not an integer. Make sense? And it's in context like this that you typically see these sets. Okay, so now, as we've already mentioned, this three-dot notation, that's very imprecise, and we want a more precise way to talk about sets, even infinite sets. And so we have what we call set builder notation. Set builder notation is a set of all, and you put some dummy variable, such that that dummy variable satisfies some condition. So some dummy variable, like x, then over here is going to be some predicate in terms of x. And so it's going to be the set of all things that make our predicate or our condition true. That's what it means. So let's get a more concrete example. So when we think about the natural numbers as a set of numbers 0, 1, 2, 3, 4, 5, etc., right? Another way we can say that is the naturals are the set of all numbers. Here's our dummy variable. The set of all x, some dummy variable. Doesn't matter what symbol we put there. I chose x. It's the set of all x. We read that colon as such that. So the set of all x such that x is an integer and x is greater than or equal to 0. So take all the things that are integers greater than or equal to 0, and you'll be left with the natural numbers. There's an example of set builder notation. Let's look at another way that we could define the naturals. This is to show some other common notation for set builder notation. Oftentimes, when we're defining a set using set builder notation, if I started with all the x such that x is in a set and some other condition about x, when we do set builder notation, it's often the case that we just take that and write that first. So now here's how we read it. What are the naturals? The naturals are the set of all integers such that that integer is greater than or equal to 0. So when you have dummy variable colon, instantly saying the dummy variable comes from some set, we often just say the dummy variable from some set. So this is saying the identical thing to this, just a little bit more condensed notation. That make sense? Mm-hmm. Okay, let's look at another one. Let's come up now with the set of all even numbers. Even integers, I should say. When you think about the evens, you typically think about integers. I don't know if you were already thinking that, but we'll say the even integers. So I want the set of all even integers. What's that going to be? That's going to be the set of all n, such that, how do you know that a number is even?
It's divisible by 2.
It's divisible by 2. Or in other words, 2 times some integer gives you the number in question. How do I know that 6 is even? Because it's 2 times 3. How do I know that 30 is even? Because it's 2 times 15. If I can represent my number as 2 times some integer, then it's even. 2 times an integer is always even. Okay, so my evens are the set of all n, such that n is equal to 2 times k, where k is some integer. Pick some integer k, multiply it by 2, it gives you an even. Take the set of all those things, now you have the set of all evens.
So does comma mean where?
You can think about it as where, or you can think about it as and. So n, where n is equal to 2k, and k is an integer.
So why would you choose that over the upside down v?
I could have put an and there just as well.
Yeah.
Okay, so now let's try one. So now I wrote out this set for you. We have 0, 1, 4, 9, ... What's the pattern?
They're all perfect squares.
They're all perfect squares. This is 0 squared, this is 1 squared, this is 2 squared, this is 3 squared. So what would the next number in the pattern be?
16.
16, then 25, 36. Everyone get the pattern?
Mm-hmm.
Okay, so now let's write this out with dummy notation. How might we write it?
It would probably be close to the evens, except for instead of n equal 2k, it would be n equal k squared.
So you want to say it's a set of all n such that n is equal to k squared,
Where k is an integer.
and comma, pick one or the other, comma, k is an integer. And that works perfectly.
Could you also do, I guess you could also do natural number instead of integer. and
Yeah,
k
notice that we don't, if I pick k to be -3, and I pick k to be 3, those both give me the same thing. There's nothing wrong with this definition, but like Emma just realized, we could also replace that with the naturals, and we get the same thing. Take any natural number, square it, it's in here. 0 squared's in here, 1 squared, 2 squared, 3 squared, etc. Make sense? Okay, so that's set builder notation. We won't see a ton of it, but when we do see it, it's good to know what it is. And I should say, we're kind of doing a deep dive really quick into set theory and functions. And then when we get to the actual textbook, it's going to start out like it gets a lot lighter and slowly delves back down to the depths that we went to. So it's like we're going to do a quick deep dive, and then it's going to get kind of easier, and then we'll go back down. That's kind of what's happening. Okay. So some relations on sets. First one is equals. What does it mean for two sets to be equal? If I say that set A is equal to set B, what does that mean? They have the same elements. It means that everything that's in A is in B, and everything that's in B is in A. Right? And that's what this dense notation says. And I intentionally wrote the dense notation rather than English because we've got to get to the point where we're comfortable reading dense notation. So let's read it. It's the set of all x in A, where x is in B, and it's A is equal to B, provided that for all x in A, x is in B, and for all x in B, x is in A. That's how to read it. So this is true when this is true.
So by just having them in curly or in braces next to each other, it implies something's in something.
That's just the bracket.
Didn't we do? So from our example last week, one of the examples we did was something like for all x, for all y. X plus y is equal to 0, right?
Yeah.
So we're doing a similar thing here. We're saying for all x, now we're specifying what set they come from. So in logic, we didn't really specify for all x, where x is what? And you kind of inferred from context that we were saying for all numbers. So if I were to write this out more accurately now, and be more explicit in exactly what this means, I should have written it like this. For all x in the real numbers, and for all y in the real numbers, x plus y is equal to 0. And that's the proper way to write it out. This, I was making you infer from context what these x's and y's were. And you infer from context, oh, they're numbers. They're real numbers. But I was never actually explicit in telling you that.
I see.
And so last week when we were doing logic, anytime we wrote the for all, you inferred from context what we meant by that. And I never explicitly told you. From here on out, we need to explicitly tell you. In math, we need to explicitly tell you. And then eventually as the class goes on, we'll get lazy again. And you'll infer from context.
Yeah.
So first it was to not confuse you. Now you're ready to see what we actually mean, and then we'll go back to because we're going to be lazy.
It's not particularly that. It's how would that like step by step fan out?
So x in B by itself is a predicate. It's not a proposition. We can't call that true or false. Assuming you know what set B is. Now, assuming you know what set A is, if I say for all x in A, x is in B, this is now a proposition. Assuming A and B are given sets. So assume you know what A and B are.
Yes.
X and B by itself is just a predicate. It's not a proposition. For all X in A, X is in B, now it's a proposition. You could call that true or false if I give you sets A and I give you sets B. Let's do it really quick. We'll call this set right here A and this set right here B. Is it true that for everything in here, it's in here?
I got that. I'm just saying, when you're putting the two, I don't know, like propositions, essentially.
Propositions are what you can call true or false.
So the predicate.
Predicates contain variables. It's understood here that X is a variable because A and B are given to you as sets that you're saying whether or not they're equal.
Okay, but I'm just saying, if you have like one predicate in the braces and the other one in its, braces, and you don't have anything between them, you're implying that,
We're implying that this is some way paired with this. The same way that was implied that this was paired with that.
so you're saying the X is paired with Y and Y is paired with.
Yeah, we saw that this was talking about an X and a Y, and this was a quantifier on the Y, so it must be referencing this thing, and this is a quantifier on the X, so it must also be referencing this thing.
Okay, so that was just assumed, essentially, based off of the.
Yeah, it's assumed from context that you'll understand.
Okay.
So this is saying for all X in A, X is in B, and for all X in B, X is in A. So this now is a proposition, this now is a proposition, and we know how to AND propositions together.
Yeah, and I got all that. It's just I was a little confused. If you just put two of the predicates together, that it somehow would it consistently communicate the same thing, or is it just they're saying that they have some relation?
You can infer from context, since I put an AND there,
Yes.
that it makes sense what I'm ANDing.
Which I understood that.
Right. So this has to apply to this has to apply to this in order for this to be something I can AND. This has to apply to this in order for this to be something I can AND.
Okay, I'll count on that. No.
Yeah, you can count on the notation makes sense. Or I made a mistake.
Okay.
Okay, so now let's move on to subset. A is a subset of B. What does it mean for A to be a subset of B? That means everything that's in A is in B. For all X in A, X is in B. That's what it means for A to be a subset of B. If A is a set 1, 2, and B is a set 1, 2, 3, is A a subset of B?
Yes.
Yes, because everything in A is in B. What if I put a 3 in A? Now is A a subset of B?
Yes.
It's a subset?
Yep.
Yes, everything in A is in B.
I only assume that because you said less than or equal to symbol, which.
Yes, it's kind of like the less than or equal to symbol. That's good intuition. Okay, so now we have the symbol which we call a proper subset. A is a proper subset of B, means that A is a subset of B and A is not equal to B. Make sense, the difference there? And like Bryce said, you can kind of think that one's kind of like less than or equal to, and that one's kind of like just less than. Okay, so no, a common way that we think about A equals B when we're talking about sets is we think about A equals B means that A is a subset of B and B is a subset of A. If A is a subset of B and B is a subset of A, then A is equal to B. And again, less than or equals is a good parallel there. Any questions on any of those?
You can also do superset, right?
Flip it around and you can say supersets, just bring it backwards.
Right.
So yeah, that's good terminology. So if we read this as, we can read this as A is a, sorry, let's do this one. We can say A is a subset of B, or we can read it as B is a superset of A.
For flip the symbol.
Yeah, flip it around. So it's just like if I say, we can, I can read this as 1's less than 2, or 2's greater than 1. And I can flip it around and write this way as well if I want to. 2's greater than 1. So, yeah, good to know that terminology. All right. So those are our basic relations on sets. Now we're going to talk about a list. So going from a set to talking about a list. What is a list? A list is an ordered collection. For a list, rather than writing a curly brace like we did for sets, we instead write an open parenthesis, and then we end our list with a close parenthesis, comma, separated objects. Same as a set, just replace the brackets with parentheses, now you have a list. Now in a list, order does matter, and duplicates also matter. So when we were talking about sets, this set was the same as this set was the same as this set. However, when we're talking about lists, this list is very different from this list, is very different from this list. Question, how many objects are in this set?
3.
3, not 4. How many objects are in this list?
4.
4.
Oh, like an associative array.
An associative array? I haven't heard that.
An array in programming?
An array? I don't know what an associative array is.
It's a term in PHP.
Oh. Yes, this is just like an array in programming. Okay, ordered pair. Common terminology. What's an ordered pair? It's a 2-element list. It's a list that only has 2 objects in it. So every ordered pair is a list. Not every list is an ordered pair. An ordered pair is a type of list. It's a list that only contains 2 things. So I can have the ordered pair containing 1, 2. I can have the ordered pair containing x, y. I can have the ordered pair containing the set 1, 2, 3. That's one object, comma, SpongeBob. That's another object. There's only 2 things in there. It's an ordered pair. It works. Good? Now, sometimes we want to talk about a list, but we want to make it explicit how many items are in the list. So we have a notion of an n-tuple. An n-tuple is a list with n elements. If I say a 5-tuple, you know it's a list with 5 elements. Make sense? If I say a 7-tuple, a list with 7 elements. If I say a 2-tuple, it's an ordered pair. Nothing weird there? Okay, so that's the basics of sets and lists. Now we're going to move to set operations. So far, when we were talking about sets, we talked about set relations. These are things that we call true or false. A is a subset of B, that's going to ultimately be true or false. A is equal to B, that's ultimately going to be true or false. Relations on numbers, like we've already talked about, 1's less than 2, that's a relation on a number. Now we're going to move to talking about operations on sets. And it's similar to talking about an operation on a number. 1's less than 2, notice we can call that true or false. What's a common operations on the numbers?
Addition.
Addition. 1 plus 2, is that true or false? Bad question. Doesn't make sense. Plus is not a relation, it's an operation. It takes 2 numbers and it spits out a number. Make sense? So now we're going to be talking about set operations. They're going to take 2 sets and spit out a set. These spit out true or false. Those were relations on sets. Now we're talking about operations on sets. They eat up sets and spit out a set. You give it 2 sets, they put them together and spit out a set. Or you give it 1 set and it spits out a different set. We can think about a unary operation on the numbers like square root. Square root is a unary operation on the numbers. When I plug in 4, it spits out 2. Okay, so set operations. The first set operation that we're going to talk about is union. It's that U symbol. A, U symbol, B. We read that as A union B. What is A union B? So remember, it's a set operation, so it's going to take these 2 sets and union them together to spit out a new set. So A union B is the set of all x such that x is in A or x is in B. If x is in A or B, then x is in the union of A and B. So, sanity check. What's A union A?
Just A.
Just A. If I take everything that's in A or A, then I'm left with everything that's in A. Alright, let's look at a more concrete example. If I have the set 1, 2, and I union that with the set 2, 3, what do I have?
1, 2, 3.
The set containing 1, 2, and 3. 1, 2, and 3 are everything that's in here or here. Alright? What about A union the empty set?
Just A.
Just A. If I take everything that's in A or in the empty set, I'm left with everything that's in A. Any questions with the union? Okay, let's move on to, and union is kind of like the OR of set operations. OR was a Boolean operation. Did we talk about Boolean? Boolean's proposition, same thing, true or false. So OR was an operation in logic. It took two trues and spat out a true, or it took a true and a false and it spat out a true. Similarly, union's kind of like the OR operator, but on sets. And you notice the OR shows up in the definition. Okay, next one's intersection. A upside down U, B, is read as A intersect B, or A intersected with B is another way you say it. That's a set of all x such that x is in A and x is in B. So x shows up in both of them. If it shows up in both of them, it's in their intersection. So sanity check. A intersected with A is just A. If you take everything that's in A and in A, you're left with everything that's in A. Okay? Let's try this one. The set 1, 2 intersected with the set 2, 3. What's everything that's in this set and in this set?
2.
Just 2. So that would be the set containing 2. Good? Alright. And what's A intersected with the empty set? The empty set. What's everything that's in A and in the empty set? There's nothing in the empty set. So if I'm taking everything that's in A and the empty set, I'm taking nothing.
Makes sense.
Okay. So that was intersection, and that's kind of like the and on sets. And you know, and shows up in the set definition. Okay, so now let's talk about set difference. A minus B. This is not the minus on the real numbers. We're talking about sets here. A minus B is a set of all x such that x is in A and x is not in B. So you start with everything that's in A, get rid of everything that's in B, and what you're left with is the difference. Make sense? So A minus A is the empty set. Take everything that's in A and remove everything that's in A, and what are you left with? The empty set. Alright, let's try this one. The set 1, 2 minus the set 2, 3.
1, 3.
The set 1, 3, right?
Yeah.
No, the set just containing 1.
Oh, yeah.
Everything that's in this, you start out with this set, now remove everything that's in this set. So we start with this, now remove the 2's and the 3's. Okay. Make sense? Finally, if we take A minus the empty set, what are we left with? A. Take A and minus nothing, you're left with A. Okay. Now, here's a weird one because it's one that you only understand from context. It's A with a line drawn above A, and it's pronounced A complement. A complement is a set of all x such that x is not in A. Now, this one is a little bit weird because you always have to infer from context where these x's come from. So, A complement, it's understood that we're talking about some universe, so I'm going to represent that as U. It's understood from context that all these x's exist in some universe, U. So then A complement is take everything in the universe that's not in A. Take everything in the universe, get rid of everything in A. That's what we mean by A complement.
Okay.
So that one's a little bit weird because you have to infer from context what it means and what the universe is that we're talking about. Make sense?
Not really.
Well, we'll see examples of it. So let's draw a Venn diagram here. And we'll go over each of these. So here's a Venn diagram. Here's a set A, here's a set B, and here's our universe. So here's U. Use that whole rectangle. Okay, so first, let's write A union B. What's A union B? That's everything right here. Everything that's in A or in B, A union B. Right? Okay, what about A intersect B? That is just this part, their intersection where they overlap. That would be A intersect B.
Just and.
which is the and one. Everything that's in A and B. Now, what if we did A minus B? That would be erase this part and erase everything over here. A minus B is this portion over here of A. Everything that's in A minus little parts that happen to also be in B. Make sense? And then A complement. So just erase that a little bit. So A complement then is everything that's not in A. So that's everything out here in the universe. Everything that's not in A is A complement. Make sense?
Yep.
Okay. Our last set operation, and the most confusing of our set operations, we call the cross product of two sets. A cross B. Now, again, this has nothing to do with times the way you know and love times. So what is A cross B? This is a set of all ordered pairs where X is an element in A and Y is an element in B. So we're creating all the possible pairings of the elements in A and B, where A's in the first, where our elements from A are in the first spot and our elements from B are in the second spot.
These are all MySQL joins.
Kind of, yeah. So let's write out this set. So A cross B is going to be the set of all ordered pairs. So we're writing out a set of ordered pairs here. The set of all ordered pairs, where our left-hand elements come from A and our right-hand elements come from B. So a left-hand element in A is little a, and there's a left-hand element, or there's an element in there, so it might be little a, comma, and then something from here, 1. There's one element in there. Here's another one in there. A, comma 2, and then A, comma 3, and then B, comma 1. Oops. And comma, B, comma 2, comma, B, comma 3.
So you couldn't.
And that's
go,
everything in that set.
So you couldn't go like 1 comma A, unless you
No.
go B cross A.
It's the set of all X, comma Y's, where X comes from the first set, and Y comes from the second set.
Okay.
So it has to be in that order. And as you just noticed, A cross B, that was weird, A cross B is very different from B cross A. If we would have done B cross A here, that would have been equal to the set containing, our first element could have been something like 1A, comma, then 1B, then we could have done 2A, 2B, etc., right? That's cross product. So that's the last set operation we'll talk about. But it's going to be the most confusing one.
Really quick while we're talking about cross products and lists. Is there, in mathematics, is there a natural notion of an indice in a list, or is that only through cross products? Or an index and indices? So if you have a list, say of the numbers 1 through 10, is there an index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or does that only happen when you multiply it by the set of the natural numbers? I mean,
Typically, when you're talking about an index, it's in reference to what we call sequence. And a sequence is a function whose domain is the natural numbers.
okay. That makes sense.
Yeah.
I'm trying to pull back from when you talked last time.
Yeah. Anyways, so there's the cross product. And that's kind of it for the basics of set theory that we'll be covering here.
I had to use that logic, and I'm trying to figure out every possible scenario.
Oh yeah, let's do a quick sanity check really quick. If A has 2 elements and B has 3 elements, then A cross B has how many elements? 6. Because we compare A with 3 things and we compare B with 3 things. 2 times 3 is 6. Okay. So now we'll move on to talking about, well, we'll be working our way up now to talking about functions. And before we talk about functions now, we need to talk about relations. So this next part, big picture, what we're going to be talking about is functions, but first we need to briefly talk about relations. Now, you might notice that we already talked about a relation in logic. So why am I talking about a relation again? It's because now we're going to create a more restrictive notion of what we mean by relation. Everything that we mean by relation in math also counts in logic. But not everything that counts as a relation in logic counts as a relation in math. Math is more restrictive than logic. Logic is broader than math. So when we say relation in math, we're going to mean what I give you here, but we're going to see it's logically equivalent to what was meant by a relation in logic. Every time we talk about relation in math, you can still think about it as relation in logic, and it works. And we'll make that make sense. Do you remember what a relation in logic was?
It has two variables.
What has two variables?
It's a predicate that...
A predicate with two variables. A predicate that takes two variables, we call the relation. And we'll see how that notion is captured by a relation in set theory. Okay, so what's a relation in set theory? It's just a set of ordered pairs. That's it. It's a set where everything in the set is an ordered pair. That's a relation. We'll make this connect here in a second to relations way we've been talking about before, but first let's just get used to the actual definition. So I have a set containing the ordered pair 1, 2, squared triangle, 3, 4, end set. So here's a set right here. Is this a relation?
Yes.
Yes. Everything inside this set is an ordered pair, so it's a relation. Here's another set. The set containing AB, 2, 3. Is this a relation?
No.
No, this right-hand thing is not an ordered pair. That is not a list with two elements. That's a set with two elements. A set with two elements and a list with two elements are not the same thing. Good? Okay. What about that set? Is that a relation?
Yep.
Yes.
Yes?
It's a subset of a relation. But I don't think it is a relation.
It
It doesn't have ordered pairs in it.
Is everything in there an ordered pair?
Yes.
Yeah.
Oh, okay, fine.
Yes, everything in there is an ordered pair.
How is it?
There's nothing in there.
Vacuously
That term,
true.
vacuously true. Crap.
It satisfies the condition vacuously. That is a set of, and you can call it a set of whatever you want. It's a set of ordered pairs. It's a set of stars in our solar system. It's a set of anything you want.
It's a set of lists.
Yeah.
And that means it's not a relation.
Is everything in there an ordered pair? You can't say, well, that contains ordered pairs, and so it doesn't contain three tuples, and so it's not a set of three tuples. You can't use that kind of logic.
Okay.
Seemed like you were kind of going down that road.
Starting with the false statement, so it doesn't... You can
That's
do anything you want.
sophistry.
Um,
Those are kind of arguments you make when you're trying to confuse people.
I have a couple questions.
Go ahead.
Is an ordered pair and not an ordered pair, is a list an undefined term like a set is?
No. So technically,
define it in
we
terms of
define
sets.
higher lists in terms of ordered pairs, and we define an ordered pair, the set theoretical definition, and we won't bother with it here, but you saw it when we went into topology. Its definition is a set A, comma, and the set containing A, comma, B.
Oh, that's right.
And so that's its exact definition, and for the purpose of this class, we don't care, but just reminded people who, when we went through set theory axiomatically, yes. And so it's a good point that I talked about sets at one point, and then I started talking about lists somewhere else, and yeah, I told you every mathematical object is a set. It's true that every mathematical object is a set, and everything can be reduced to a set. It might not make sense to you how that's the case, so you kind of have to take my word for it, that everything is fundamentally a set. Let me show you one more, just to send it home. What about the number 1? Is that a set? Yes. What's the definition of number 1? It looks like this thing. And there's 1. Oh, sorry, that's 2.
What?
Oops. So that's 2. Does it make any sense? No, doesn't have to. The point is, everything we talk about in math is fundamentally sets, including lists. But you don't have to remember that. You don't have to know their set definitions. You just kind of need to know enough to work with them.
This is kind of, I have a question that's kind of beyond the scope of the class, so you can just say no. But how do you derive set notation from logic notation? Okay, and I know they're very closely connected, but
We still have axioms.
you cannot. The reason I'm asking this is because you can't really get the logical definition of a relation in set theory notation, but you can. It seems like you should be able to encapsulate everything that's set theory in logic, right?
You can.
So is there a way to use logical notation to define what a set is?
No. A set is an undefined term.
Right. That's what I was wondering.
So there's no way to define it. These notions just have their logical equivalent. What we mean by a relation in set theory is more restrictive than what we mean by a relation in logic.
Right.
And so it still satisfies everything that's relation in set theory is still a relation in logic, and so all the logic that you use with relations still works.
But there's no way in set theory to capture what a relation means in logic. Exactly. Because it's more restricted.
Right. Yeah, by its nature, it's more restricted. Okay, so what's a relation? A set of unordered pairs. That's it. That's all it is. Relation, not a relation, relation. Vacuum state relation. Okay, now we have a notation for relations. Remember that relation is a set of ordered pairs. There's only ever, it's a set of two things. Two things, two things, two things, two things. So we have now some notation. So if R is a relation, R is some set of ordered pairs, then we say X is related to Y, provided that the ordered pair XY is one of the things in R. Right? So one of the relations we got comfortable with working with, one of our examples of a relation that we used in logic was the lesson symbol. And now, what is the set theoretical definition of lesson? We can say lesson is equal to the set of all the ordered pairs, where the left-hand number is less than the right-hand number. Obviously, I can't write them all because there's infinitely many.
But you could write it in.
But that would be a precise definition for what less than means. So here's the definition of the relation. So when we say 1 is less than 2, that's another way of saying 1 comma 2 is in less than.
And that goes
So that's what we meant by this notation. And notice that this is a proposition, so that is a proposition.
So it's just an infinite definition.
Yeah, there's lots of sets that are infinite, and that's fine.
But you could write it.
This isn't exactly how we would actually define this, but I'm just giving you intuition for how we could define that using sets.
Okay.
But it would be defined as a set, like that. It would be logically equivalent to that thing when we gave it a proper definition.
Yeah.
Okay, so that's why sets of ordered pairs still act like relations the way that they do in logic. Make sense? And we could also say this is logically equivalent to, well, no, I don't want to say that. Because then that's technically not true, because there's a logically equivalent way we could do this that I don't want to get into. This is good enough. Okay, so now we're ready to talk about a function. The same way that a relation is a special type of set, a function is a special type of relation. A relation was a set with some condition, everything was an ordered pair. A function is a relation with some condition. What's the condition? So a relation f is called a function if anytime you have a, b in f, and you have a, c in f, then b is actually equal to c. So if a was paired with b, and a was paired with c, then b and c have to actually be the same thing. Another way to say that, for those of you, terminology that you've heard before, is every input has a unique output. If your input is a, and these are two things that a goes to, then those two things have to be the same thing. A has to be mapped to one and only one thing in order for it to be a function. So let's look at a concrete example and then read that definition again, and I think it'll click. So let me push this enough that we can see the example and still the definition. Too dark. Let me see. Okay, there we go. Okay. So let's look at an example. So f is this relation right here. It contains the order pair 1, 2, 2, 3, 3, 3, 4, 7. Question, is f a function? Why not?
Yeah, it is.
Yeah.
Yes.
Oh, right? No.
F is a function if every input goes to one and only one output.
Yes, it is.
Oh, no.
What does 1 go to?
2,
2. What does 2 go to?
3,
What does 3 go to?
3,
What does 4 go to?
7.
Every input went to one and only one output. So f is a function.
So the first in the set, or in the ordered pair has to be unique, essentially.
Every left-hand element has to be paired to a unique right-hand element.
Right.
Question. Is that still a function?
Yes.
We paired 2 with 3, and we paired 2 with 3 again. So we're good. 2 still goes to 3. And in fact, duplicates don't matter in a set. So I actually didn't even change the set. By adding 2, 3 again, I didn't change the set. Make sense?
Okay.
So f is still a function. Every input has a unique output. Anytime you have two inputs that are the same, their outputs better also be the same in order for it to be a function. Let's look at g now. G, is that a function?
No.
No. We have 1 goes to 2 and 1 goes to 3. So it's not a function. We had 1, 2, we had 1, 3, but 2 is not equal to 3. So it doesn't satisfy the condition of our definition. All right, what about h? Is h a function?
Yes.
You sure?
Yeah.
Is Bob a square?
It's a good question. We'll assume not. So square goes to triangle, 1 goes to square, and Bob goes to frame. So we're good. Every input has a unique output. Now, another way that you've seen some of these functions written is we write all the left-hand elements over here. So let's write out f really quick. So we have all the left-hand elements are 1, 2, 3, 4, and then 2 again. So there's all our left-hand elements.
That's really just the set A, right? From your relation.
If you're jumping ahead to thinking about this type of notation,
Yeah,
no.
That's, okay, gotcha.
Okay. Oops. Oh, no, we're fine. And then over here, we're going to write out our right-hand elements. 2, 3, 3 again, 7. So now we're going to write the function f pictorially. We had 1 goes to 2. We write that as an arrow like that. We had 2 goes to 3. We had 3 goes to 3. And we had 4 goes to 7. We loosely call these things the inputs, and we loosely call those things the outputs. Loose terminology. Every input has a unique output.
Why do you refer to it as loosely?
It's not a properly defined term. Input isn't a mathematical term.
Oh.
We call this set the domain and this set the image. But
Oh.
The image?
Yeah.
Not the range.
range and image mean the same thing.
Okay.
Range is what little kids say. Image is what big kids say. It's the
You wonder why they have
Separate the
different
cool
terms
kids
for it.
from the nerds.
yeah. It's just that. I mean, it's hard to know the history of how these things evolve. But your lower textbooks, for some reason, they say range. Your higher textbooks, for some reason, they say image. And so, since I've done more higher textbooks and lower textbooks, I say image. Okay. G now. Let's write that one out really quick. So we had 1 and 2 over here, right? 1, 2, 1. And then over here we had 2, 3. With me? And so we had 1 goes to 2. We had 2 goes to 3. And then we had 1 goes to 3. Notice that we have one input going to 2 different outputs. Invalid, that's what makes it not a function. Every input has to have a unique output for it to be a function. And I don't think we need to draw out H, right? Think you guys get it? Okay, important, I know you got the intuition for it. Force this definition to click in your head and force it to make sense. And you get comfortable with this dense notation early on before we get to the hard stuff. So let's read it one more time. A relation f is a function if anytime you have a, b, and f, and a, c, and f, b is equal to c. The things they're paired to are the same thing.
Inputs and outputs.
If you find two ordered pairs with the same input, then they better have the same output. Otherwise, it's not a function.
Right.
Does that make sense? Okay. More notation. If f is a function and a and b are one of the ordered pairs in f, then we write f of a is equal to b. And you've seen this lots of times. We say f of a is equal to b. Another way you can think about that is the right-hand element of a is b, because ab was in f. So let's get comfortable with this. We'll do it for this example up here. So what's f of 1? 2. Because when I go to f and I find the right-hand element paired with 1, it was 2. What's f of 2?
3.
What's f of 3?
3.
Notice those have the same output, that's fine. We just wanted each input to have a unique output. We didn't say every output has to come from a unique input. So, perfectly fine. What's f of 4?
7.
Wonderful. What's f of 5?
6.
Bad question. Doesn't make sense. 5 is not in the domain.
No.
Sorry, we haven't defined domain yet.
Yeah.
5 isn't paired with anything. Bad question. Okay, let's move on to G. What's G of 1?
2.
Doesn't make
3.
sense.
2 or 3? Which is it?
23.
It's not a function. So
It doesn't make sense. Notice that we said this notation is for when we're talking about a function. G is not a function. So it's invalid to try and apply this notation to G. It was also invalid to ask f of 5. Bad question. Notation doesn't make sense in that case. All right. What's h of square?
Triangle.
Wonderful. What's h of 1?
Square.
And what's h of Bob? Obviously.
did you want to also talk about inverse function notation?
No.
over here?
No, we don't need anything that advanced. Okay. So, I think you're pretty comfortable with that notation. Okay. Some logically equivalent ways of saying that f is a function. We work with functions a lot, so it's nice to have a couple different ways of thinking about what's a function inside your head. So a relation f is a function provided that anytime your inputs are equal, then your outputs are also equal.
Yeah.
If a is equal to b, then f of a is equal to f of b. Same input means same output. Make sense?
Why are we defining function twice?
Not really defining it. This was its definition. Notice that this is using notation, which already presupposes.
Okay, I see.
It's just another way to help you think about it with the new notation. Okay, so now let's think about, what was I after here? I know what I was after. Okay, so here's a function now, written out. And hopefully you notice a pattern with the function. Negative 3 goes to 9, negative 2 goes to 4, negative 1 goes to 1, 0 goes to 0, 1 goes to 1, 2 goes to 4, 3 goes to 9. What are we doing?
It's basically a parabola with integers.
We're pairing every integer with its square.
Right.
Alright? So let's try and write this out with set builder notation.
Does that mean it would look like a bunch of dots in a parabola, or would it be a line?
We're not going to talk about graphing this thing. We're not talking about parabolas, we're not talking about graphs. We're just talking about... This is one of the reasons that these classes are so hard. It is because there comes a point where you get comfortable enough with lower level maths that you think more about it than you should. And so you see this and you instantly start thinking about a parabola on a graph rather than literally just this set as it is.
Well, I mean, it's basically the same thing.
A parabola is a geometric object.
The function that produces.
I know.
coordinate plane.
They are related. But think about really the leap you're making there in your mind.
Yeah.
Here we are in set theory, and you want to throw geometric objects at me.
Right.
Right?
Connections.
Making connections, and it's not bad to make those connections, but it often makes the student use bad reasoning in how they reason about something's valid. So early on proofs, kids often get stuck because they're not sure what they can use. Because they kind of want to use these higher level things, but those higher level things were built from the things that they're supposed to be proving.
Right.
And so it's hard for them to get started. And that's in the sense that these classes are hard. They're hard because they're so foundational that it's hard for students to keep track in their heads of what they can and cannot use.
Yes.
And so that's the sense in which these lower level math classes are hard. Like real analysis was hard.
Yes. Because you tried to use addition and you realized you couldn't use addition.
Anyways, so let's try and write this out with set builder notation.
So you'd say x such that x is in z and I guess it'd be AB, not x, because it's order pairs. So you'd say an order pair AB such that
I'm going to use xy.
xy works
So it's a set of all ordered pairs xy such that
they're integers, or such that x is an integer at least, and y is equal to x squared.
Perfect.
Does a comma work, or do you have to use the and symbol?
You can use the and or the comma. Means the same thing.
Okay.
A comma in that context means and. Sorry, I was about to give a bad example. So I'd say it's like a condition in programming. You can use ands or commas for some languages.
For some languages.
For newer languages, older ones you can't. Anyways, yeah, those are the same. So yes, you were perfectly right. This is exactly how we would write this. Now, this is kind of a lot for writing out this thing, right?
It's better than what you wrote before.
It's much better than what we wrote before. But we have an even shorter hand way of writing these types of functions.
Right.
And the way that we write this function now, right here, is we would write it as f of x is equal to x squared. The right-hand thing is equal to the left-hand thing squared.
Don't you still have to specify that it's integers?
It's usually inferred from context. I just wanted to show you something that you've seen in algebra 100 times.
Right.
So in algebra, you saw that 100 times. Now in algebra, the only difference is replace this with r, and it was understood that you were always talking about the real numbers, always and forever. So when you saw f of x equals x squared, that was shorthand for the set of all ordered pairs xy, such that x is in r and y is equal to x squared, which was shorthand for the list of all the ordered pairs of things that satisfy that thing. So every time you wrote that, you were really writing out an infinite set. And it was shorthand for that infinite set. That make sense? Just trying to connect the set back to the notion you probably already had in your head from algebra of what a function is. Good? Slow nod? Yeah? Alright, so let me move down so that I can see that column and a bunch of the whiteboard. I can still see that line. And I still need to move it further, so. Get to there and move. All right. So, more definitions for things you already know about functions, but remind you of it. If f is a function, the domain of f is a set of all left-hand elements, or all the inputs. Put all those together in a set, we call that thing the domain. To write it out explicitly, the domain of f is a set of all x, such, we'll read that as a where, it's going to read better in English. So it's a set of all x where there exists some y such that x is paired with a y in f. take all the x's where there exists some y such that x is paired with a y in f. Those are all the things we're talking about in the domain.
When do you use the one, only one, where there's a exclamation mark after the e? Because you can't move over to it.
If I can find some y such that x is paired with y, then x is in the domain.
Oh, yeah, okay. Similar.
Is domain only used for function, jargon?
Yes, domain is functional jargon. The domain always means the domain of a function. Doesn't make sense outside that. Good point. Okay, similarly, we have the image, or what you often call the range, and it's the right-hand element of a function. Or, to be very explicit, the image of f is defined to be the set of all y where there exists some x such that x is paired with that y in f. Take all the things that are somehow paired to, that's your image. What don't you like?
I'm trying to think about it.
Okay, yeah, just absorb it. This notation's dense until it's not.
What about? No, that makes sense.
Make sense? Cool.
No.
No. Yeah.
What if you have an x that goes to two different ones?
There just has to exist some x such that it's paired with that y. So pick your y, 5. If I can find an x paired with it, then it's in the range, or then it's in the image. If I can't find an x paired with it, then it's not in the image.
Oh.
If I can find 10 x's paired with it, fine. I just need to be able to find at least one. Remember, there exists means there's at least one.
Yeah.
So it's all the y's where there's at least one x such that x is paired with that y. There exists at least one x paired with the y. Then y is in the image. Otherwise it's not. Make sense?
Yeah.
Okay. So now the hardest notation that we see with functions, which is this notation right here. F colon A arrow B. Now arrow is not the implies arrow. This is all one piece of notation. So we read this as F is a function from the set A to the set B. A is always a set in this notation, B is always a set in this notation, F is always a function in this notation. So whenever you see that right there, you instantly know F is a function from A to B. And we'll give you more context for what we mean by from A to B, but understand function, set, set. Good so far? Okay. So, F is a function from A to B. What does that mean? That means F is a function whose domain is A and whose image is a subset of B. Not whose image is B, whose image is a subset of B. Weird? I know. But that's what it is. So, F from A to B, what do you instantly know about F? You know the domain of F is equal to A, and you know the image of F is a subset of B, and you know F is a function. That's everything you know from this notation right here. So it communicates a lot. F is a function, A and B are sets, the domain of F is A, and the image of F is a subset of B. That's everything that notation's telling you. Very handy notation. But it says a lot.
Is that like quotation marks or a mark or something that we?
My quotation is, I'm giving you a sentence now for how to read that thing. So, F from A to B, that is, F is a function from A to B. That's how we say it.
Is there, just for my personal interest, is there a way to write that in set builder notation that captures that exactly?
Is there a way?
So,
No, you cannot just from writing the function itself make explicit the A to B, and we'll see that.
so how do you get a rigorous definition if you can't?
We won't worry about that, but you can. Okay, so let's do an example with this really quick to help you make sure you understand the notation. So A, we're going to call the set 1, 2, 3. B, we're going to call the set 4, 5, 6. I'm going to define f now to be the function 1, 4, 2, 5, 3, 6. Question, is f a function from A to B? Yes or no? You sure?
Yeah.
What's the domain of f?
A.
1, 2, and 3, which is A. What's the image of f? 4, 5, and 6, which is a subset of 4, 5, and 6. So yes, it satisfies a condition. F is a function, its domain is A, its image is a subset of B.
How do you get it where it's not a subset of B?
We'll see.
Yeah, we'll see examples of all these. Next example, G. G, 1 goes to 6, 2 goes to 6, 3 goes to 6.
Yes.
Question, is G a function from A to B?
Sure is.
3 conditions. Is G a function? Yes. What's the domain of G? 1, 2, 3, which is A. So we're good. What's the image of B? The set containing 6. Is the set containing 6 a subset of the set containing 4, 5, and 6? Yes. So G is a function from A to B. Let's look at the next one. H. 1 goes to 4, 2 goes to 5, 1 goes to 6.
No.
It's not a function. It's not a function.
It's not a function.
Yeah.
Correct, it's not a function. We have 1 goes to 4 and 1 goes to 6. It's not even a function. How can it be a function from A to B? So no.
It also isn't the set A, so it wouldn't even then. Even were it to be a function, it wouldn't.
Even if it were a function, it still wouldn't be a function.
Would be a function from A to B.
Oh, I see what you're saying. Okay, next, I.
Oh.
1 goes to 4, 2 goes to 5. Is that a function from A to B?
Yeah. It seems like it.
We have a yeah, we have a no.
Yeah.
Because it has to be from A to B.
What's the domain of I?
1, 1 and 2.
Is that equal to 1, 2, 3?
Okay, so it has to be the exact.
No. So it is not a function from A to B. The domain has to be A, and the image has to be a subset of B.
Got it.
Those are weird. And then for Chandler, we'll do one more here. And I'll really quick throw on I'm going to switch A to be 1, 2, 3, 4, and B to be 4, 5, 6. You with me?
Yep.
So if I would add it here, 4, 6, is f still a function from A to B?
Yes.
Yeah.
Okay, now if I replace that 6 with a 7.
No.
Okay, because now 4, 5, 6, 7 is not a subset of 4, 5, 6.
Yeah.
Okay. Think we got the notation? F a function from A to B?
Roughly, yeah.
Roughly? Good enough. Alright, let me switch this back, how I have it. Might reference this later. So put that back to just 3. So I think in this next example, I'm probably actually not, never mind. Alright, so now, when you were taking your algebra course, and you were shown something like f of x equals x squared, that is because the author was hiding you from the full notation of what we mean. Here's what the author really should have written in the book, and when you get to higher level math textbooks, here's what they write. F is a function from the real numbers to the real numbers by f of x equals x squared. And it's explicitly stated that we're mapping from the real numbers to the real numbers. I should also call that statement. I might accidentally call functions maps all the time. Logically equivalent. What do you mean by map? A function. What do you mean by a function? A map. It's just other terminology that's used a lot. I may accidentally say it.
Map.
I'll try to always say function, but yeah, I may probably say map. When I say map, I mean function.
So that's MAP.
M-A-P, map.
It's like when you have the two lists there, and you can map each element.
Yeah, this maps 1 to 4, 2 to 5, 3 to 6 is one way that we'd say that. And that's where the mapping terminology comes up. So, just in case I accidentally say it. Anyways, so here's what was meant in your algebra courses that you took. every time you saw f of x is equal to x squared. Okay, so now f of x equals x squared, that's our function. What is the domain of that function?
All the real numbers?
All real numbers, R. What's the image of that function?
Positive numbers and 0.
Not R. I can never get negative 4 out of this thing. What number do I square together to get negative 4? 2 squared is 4. Negative 2 squared, still 4.
2 squared I.
That's not a real number.
Yeah.
So it's only the numbers 0 and up. Now, you're probably not used to this notation. If you're not, that's fine. We're not going to go over it, but here's the way that we say that. It's all the numbers from 0 to infinity, including 0. Maybe you've seen that before, maybe you haven't. We're not going to use interval notation ever in this class hardly, so if you haven't, that's fine.
R plus union, the second being 0, right? Technically.
Do what?
R, so like R plus, the positive real numbers.
Oh, but no, that seems clearer.
That's, I don't know, but that would
The
be.
plus up there seems more confusing to me, so I'm not even going to shell that.
Can you read that one more time, the example? Just read it out loud.
This? F is a function from the real numbers to the real numbers by f of x equals x squared.
And the image is a subset mark.
Let me say it with the map word, and maybe the by makes more sense. F maps from the real numbers to the real numbers by f of x equals x squared.
Yeah.
But this just tells us what our domain, this just gives us image about our domain and our, did I say something weird? Restart. This just gives us information about the domain of our function and the image of our function. It does not tell us how the function is actually pairing numbers.
Okay.
So the numbers we're mapping from are right here, the numbers we're mapping to are right here, and the map that we're using is right here. Our method of mapping. Good?
Mm-hmm.
Okay. So now with this notation, we have a couple properties that a function can have. One of the properties a function can have is onto. So a function f from a to b is onto, provided that the image of f is actually equal to b. So when you see f from a to b, you know that the image of f is a subset of b. If I also tell you that f is onto, that means that the image of f is actually equal to b. So it's not just a subset, it's actually equal. So let's look at f and g over here real quick and see if either of them are onto. So f maps 1 to 4, 2 to 5, 3 to 6. Question, is this onto?
Yes.
Mm-hmm.
Yes, because the image of f, 4, 5, 6, is equal to the set b. So f from a to b is onto, I could write right there, and it'd be true. Now let's look at g. G, 1 to 6, 2 to 6, 3 to 6. G is a function from a to b, but it is not onto.
If you switch up the order of the ordered pairs, would it still be onto? If you have all the,
If I flip those,
no, if you do like 2, 6, and then 1, 6, and then, or 2.
order inside sets does not matter. So it just so happens that I wrote what 1 goes to first and 2 and 3, and that's just for readability purposes. But yeah, I could have written this term first, this term second, this term third, doesn't change the set. Order doesn't matter in a set. Good question.
I'm confused how you would communicate onto when the term, the structure is exactly the same as far as the symbols and what do I call it?
You have to specifically say is onto.
Actually, okay.
Yeah, you,
So there's no symbol for it.
no, there isn't a symbol to say and it's also onto.
Yeah.
Alright, so let's look at examples from functions that you know and love from back in your school days. So we're looking at f is a function from r to r by f of x equals x squared. Is this onto?
Yep. No. No, it's not.
No.
We just found it out.
We can't spit out negative 4. Negative 4 is in the real numbers. Negative 4 is not in the image of this function. This function cannot spit out -4. So it is not on 2. All right, let's look at g from r to r by g of x is equal to 2x plus 1.
Yes.
That one is.
This one is. For those of you who want to think about geometrically, this is a line. A line has an output everywhere.
With an offset of 1.
Huh?
Yeah, just with an offset.
Another way that you can think about this is pick any output and I can tell you the input to plug in to get that output. So you say, okay, how do I get the output 7? I say plug in 3. You say, okay, how do I get the output -7? Plug in -4 for x. And I could give you the formula, but how I'm figuring that out doesn't really matter for this class. Just giving you an example of on 2. And if that one's throwing you off, but you understood that one, you're fine. Okay, another property that a function can have is it can be 1-to-1. A function f is, and oftentimes we write 1-to-1 this way, because we're really lazy and we don't know how to spell that out. So we write the number 1 dash the number 1 for 1-to-1. So a function f is 1-to-1 provided that anytime AC is in f and BC is in f, then A and B are equal. In other words, if the outputs are equal, then the inputs have to also be equal in order for the function to be 1-to-1. So a relation was a function if for every input you had a unique output. And now a function is 1-to-1 if for every output you have a unique input. So a bunch of different ways we could also say that is, if your outputs being equal implies your inputs are equal, then it's 1-to-1. Or, if you like to think about it in terms of the contrapositive, here's thinking about this as a contrapositive. Remember, A implies B is the same thing as not B implies not A. If I'm wearing shoes, then I'm wearing socks is the same thing as if I'm not wearing socks, then I'm not wearing shoes. They'll say the same thing. So f of A equal to f of B, outputs being equal implies inputs are equal, is another way that you can think about a 1-to-1 function. Or you can think about it as, if you have different inputs, then you're guaranteed to get different outputs.
So with 1-to-1, there's no duplicate numbers.
If you get rid of all redundant elements.
Yeah.
Correct.
Would that 2x plus 1 be considered a 1-to-1?
This one is 1-to-1.
If you want to think about it geometrically, you can use the horizontal line test.
Yeah, vertical line test for a function, horizontal line test for a 1-to-1 function. Okay. Let's write out pictorially to see 1-to-1 when we write out functions this way. So I've got, here's a set A, here's a set B, and I'm just going to make up some function to map A to B. So I'm going to map 1 goes to 2, 2 goes to 1 goes to B, 2 goes to A, 3 goes to C, and 3 goes to D, and 4 goes to D. Question, is that a function?
No.
No, because I have one input going to 2 different outputs.
Also function.
So that's not a function.
A function.
So now we get rid of that. Now is it a function?
Yes.
Yes. Is it a 1-to-1 function?
Yes.
Yes. Sorry, I erased the wrong arrow. I meant to erase this arrow. Is that a function?
Yes.
Yes, every input has a unique output. Is it a 1-to-1 function?
No.
No, because an output is coming from 2 different inputs. Writing our function notation, what is f of 3 equal to? D. What is f of 4 equal to, if this is the function f?
D.
D. So, notice that f of 3 equals f of 4, but 3 is not equal to 4. In order for it to be 1-to-1, anytime the outputs are equal, the inputs have to be equal. Here we had equal outputs, but different inputs. And so it's not 1-to-1, because this is not always the case. Equal outputs does not imply equal inputs. And you need to get past just understanding it from the picture and being able to understand the notation. That's going to be the hard part early on, because as you get confused in this class, it's going to be the notation that throws you off. Because it's not that the ideas are going to get super complex. So you need to make sure you understand notation. Think we're good? Can you draw more examples? All right. So then the last property we'll be talking about on functions is, let me pull this way. Okay. The last property we'll be talking about on functions is called a bijection. So a function can be a bijection. What is a bijection? So a function f from a to b is a bijection if and only if it is 1 to 1 and f is on 2. So if it's 1 to 1 and it's on 2, then it's called a bijection. So come back to this picture. If I get rid of this line and I make 3 point to c now, notice what is the image of f? It's A, B, C, and D. It's the entire set B. Right? So f is on 2. And notice that every output comes from a unique input. So it's 1 to 1. So this is a bijection. A bijection maps every element in A to one and only one element in B. And every element in B comes from one and only one element in A. So if I were to add to B some other symbol E, is this function 1 to 1?
Yes.
It's 1 to 1. Is it on 2? No, so it's not a bijection. Should I say it? I'll say it. And so, just so you know, the way that we determine whether two sets are the same size is if you can create a bijection between them.
That makes sense.
I can't create a bijection from A to B, so those sets are different sizes. If I get rid of E, now I can create a bijection from A to B. And so they're the same size. That's technically what we mean by two sets being the same size. We call it, there's a set isomorphism.
Is that the
Just because we like complicated words that make it sound smart.
formal definition of is that? So
Yes, that's exactly what we mean by our two sets the same size.
There are valid other ways to do that though, to show that the set is the same size.
How else would you do it?
Counting.
When you count it, you're showing it's the same size as that set, because remember, a number is a set. And the number 2 has 2 elements in it.
So it's not.
And so when you say the count is 2, you're saying that set has the same size as 2. So yeah, that's how we determine the size of sets.
Right.
Bijections.
Right. Remember that. Lots of proofs.
Yeah, I think we did a bit with that in topology. Can't remember.
Well,
Did you do topology?
I didn't know.
Right.
Discrete math, we did that like 100,000 times.
Oh, yeah, we probably did a lot of
I
that.
remember there was a question on a test I got wrong because of that.
Nice. Worked really well.
Okay, so now, not really introducing a lot of new stuff anymore. Now we're just going to do a bunch of examples and make them slightly more complicated to make sure you understood what we covered today. Make sense? So now let's go back. Here's the set A, here's the set B. You remember what we mean by A cross B?
Yep.
So tell me what to write.
1x ordered pair,
1x,
2x, 3x, and then 1y, 2y, 3y.
wonderful. All right, and if we did B cross A, what's the difference?
They're switched.
Yeah.
The elements are switched.
Oh, yeah.
So now it's just going to be x1, comma, x2, and I can just rewrite those switching the order.
Yep.
And that's the difference.
Mm-hmm.
Notice that there's the same amount of elements in both sets. We just flip the orders. Now we could have also done something like A cross B cross A.
I assume you just go in order of left to right.
You can go in order of left to right or right to left. Doesn't really matter,
Are they the same? I guess they are the same in that case.
but it's understood left to right. So we're gonna do A cross B and then cross it with A. But you can think about,
If you had
it gives you 3 element lists.
If you had 3 sets, it wouldn't do that though, would it?
Well, let's write the first element, and then we'll see.
Does that mean it should be twice as long?
No.
In this case, twice as long, because, oh no.
It'll still have.
Oh, no, I'm not writing that one, way too big. Let's flip that, we'll do B cross A cross B. Okay. Because B only has 2 elements.
Okay.
So this has 2 elements, this has 3, this has 2, so the size is 2 times 3 times 2,
12.
which is 12, rather than 18. Really saving there. Anyways, so let's write an element in here. What's an element in here?
X, comma, you have to go order pair inside the order pair.
So you want something like x comma order pair.
I was gonna go.
One comma.
You want order pair first.
Yeah. So x comma 1, close parenthesis, comma, x. Now tell me if I'm wrong there. Because you said that it should be a 3 element list, but that's not the definition of cross product.
Right. So we're going to hide a technicality, because technically this is a 3 list, but I don't want you to have to think about that.
Not really.
So instead, what we're going to define this to be by this notation is, it's just going to be a 3 list. That is the definition. So we're just going to define this to be a 3 list, where the first element comes from B, the second element comes from A, and the third element comes from B. And I think that'll be easier to remember. And that's the way the author uses the notation.
So if you have a list that contains an ordered pair and another theme, it's just a 3. That's the definition of a 3 element list.
I don't want you to remember that this is the definition for this class.
Why?
Because we're going to use that notation in a special case to help keep track of something. You'll see right here. I don't want you to think about that as a 3 element list.
But is that the definition?
But
of a
yes.
3 element list.
So here is the definition of a 3 element list, but I want you to forget it right after I tell you, just for the sake of your curiosity. XYZ is defined to be x comma, I don't remember if it's x comma y or x comma yz. I think it's this way.
Does it make a distinction?
I'm sure they're logically equivalent,
Okay.
but I'm not positive. But yes, technically, you would define your higher order list in terms of ordered pairs. You define your ordered pairs in terms of sets, so they're really all sets.
Right.
Now forget that that's the case, and pretend that they're different somehow. Okay. So here, when we have B cross A cross B, this is now going to be a set of 3 tuples, list with 3 items in it, where the first item comes from B, second item comes from A, third item comes from B.
Gotcha.
So x comma 1 comma x is a valid thing in there.
And then x comma 1 comma 1.
And then we can do x comma 1 comma y. And then we can do x comma 2 comma x, x comma 2 comma y, x comma 3 comma x, x comma 3 comma y,
And forever.
x comma,
No, it's
no,
not.
now we switch to y's. And then we would do y comma 1 comma x, y comma 1 comma y, y comma 2 comma x, y comma 2 comma y, y comma 3 comma x, y comma 3 comma y. Alright, and those are all the possible ones, and hopefully there is 12 of them. 6, 12, yes. So unless we have a duplicate up there, we got them all.
Mm-hmm.
Alright, so that's what we mean by B cross A cross B. Alright, now you're also going to see this notation. You're going to see A squared. What on earth does it mean to square a set? That means to multiply by itself with this cross product. So A squared means A cross A, so in our specific case, let's really do B squared. I kept thinking A was a smaller set. So B squared, which is equal to B cross B, is equal to the set, and we have XX, XY, YX, YY. That makes sense to everyone?
Mm-hmm.
Alright, and now, we can't list them all, But let's start writing out n squared.
0, 0,
So this would have 0, 0,
0, 1,
0, 1.
0, 2,
Maybe we'll do 1, 0, 1, 1, and then we can keep on going, and I think you get it. We can write 5,064, or 5,640, and 9, etc. All the order pairs of possible natural numbers we can make.
So
And there's infinitely many.
I'm remembering, you might have to jog my memory for this question. There is a way where you do that. Okay, I'll have to come back later because it's a little fuzzy. I remember, particularly modular arithmetic, there was a different definition with when you use the integers and then you have like the space and z6 or something. But that was totally different. But for some
We'll get
reason,
there.
Oh, okay.
Okay,
I feel like there was something I'm forgetting that used that notation from somewhere.
anyways, so notation. In general, when you see the set A1 crossed with A2, crossed with A3, crossed with A4, crossed with A5, up to n of them, hopefully you can understand what this is saying. We're crossing together n sets. Well, it's n, some number. Could be 10, could be 5, could be 27. So when you're crossing together n sets, then that is going to be the set of n tuples, A1, A2, A3, A4, all the way up to AN, such that A1 comes from the first set, the first element comes from the first set, the second element comes from the second set, and the nth element comes from the nth set. And that's what we'll mean, in general, by crossing a bunch of sets together, which is exactly what we did right here.
So A1 and A2 are different sets.
Yes, they could be the same, they could be different.
That's only.
Yeah, I just remembered that. That's notation that usually takes kids a bit to get comfortable with. So I can use different letters for different variables. Sometimes I don't want to come up with a bunch of different letters, and so then I just change subscripts. So I could write x, y, z if I need to use 3 variables, or if I'm starting to feel lazy, I could write x1, comma, x2, comma, x3. And that just means 3 different variables.
Which can be very useful in large sets.
Yeah, it's useful notation, so good for you to know. So yeah, thank you for pointing that out. So the same way that x, y, and z, they could all be different, they could all be the same, they're just 3 variables. Maybe they're the same, maybe they're not, who knows. Same thing here. A1, A2, A3, all the way up to AN, they could all be different sets, they could all be the same set, any combination.
So they're not in any way dependent on each other.
They're in no way dependent on each other. They're each their own sets. And same one with A1, A2, all the way up to AN. None of those A's are dependent on each other. A1 is only dependent on A1, A2 on A2, and AN on AN, because that's the set it ultimately comes from.
Is there any reason you're switching from lowercase to higher?
Yes. Thank you again. As a matter of notation, we use capital letters when we're talking about sets. We use lowercase letters when we're talking about elements of sets. So you will never see me write something like this. And it even made you laugh because you're so used to notation. It's x is in A.
Well, hold on. If it was inside of that element was actually a set.
I will never make x a set such that this makes sense. It's not that there's anything technically wrong with it.
Okay.
There's nothing technically wrong with it. It's just a matter of notation. We use capital letters for the sets we're talking about, and we use lowercase letters for the elements in the sets we're talking about.
What I'm saying is that you could be referring to the sets inside of an element that is a set.
Oh yes, that could very much be the case.
Okay.
And yeah, notation, you can only stretch it so far before you run into it.
You can't get an element that's a part of an element, though, can you? At that point, it's a subset.
Oh.
You could have something like this. We're getting to this.
So
It's a set, but inside it is also a set.
So the first set element could
So
be.
I could be, say, if I called x the element in there. Oh, no, we need one more.
Yeah,
This is going to become.
there we go.
Why
Why are you doing 3?
So this outer one, we could call the set B. So if I say x is in B, well now x is referring to the set containing the set containing 1. And if I call the set containing 1 capital A, then yes, now we have A's and X's in B. And we could be in trouble with our notation. And that could get confusing. Fortunately, we won't be doing anything
So
like that.
that is not, that is the correct way to write it.
There isn't notation defined for this use case. I mean, it's just a convenience.
I figured it would be subset, but that makes sense, I guess.
Oh no, that's not subset, that's contained in.
Yeah.
Yeah.
Anyways,
So is lower A1 equal to upper A1?
no, lower A1 is in upper A1.
Okay,
It's an element in there.
that's confused me, okay.
A lot of notation.
The hardest thing to get used to.
For people that ultimately drop the class, yes.
Yes.
You can get the idea it's harder than the notation. But the notation is hard to get, so. Yeah, this is probably, what you're seeing right here is probably real dense for most of you, and probably aren't used to seeing something that dense. So, trying to throw the dense stuff at you intentionally so that when it creeps back up, you're ready for it. Alright, let's do another example. We're going to look at the absolute value function. We're going to look at the absolute value function from the integers to the integers. Now, I'm assuming that you know what the absolute value does, right? What's the absolute value of 5?
5.
What's the absolute value of negative 5? 5. Just spits out the positive version of the number. Okay, so let's start writing out this function. What would be some of the things in here?
1.
1. And what's the absolute value of 1?
1.
1. Give me another number.
3.
And what's the absolute value of 3?
3.
And give me another number.
Negative 6.
Negative 6. And what's the absolute value of negative 6?
6.
6. Okay, and we can keep going.
You could put variables in that, right?
Well, I just want to write out some elements in there. Just to make sure we're all on the same page. Okay, so question now. Is this absolute value function 1 to 1? It's not 1 to 1?
No.
No, why is it 1 to 1? Because 3 goes to 3, and negative 3 also goes to 3. So we have 2 inputs going to the same output. 1 to 1 means every output comes from a unique input. This output comes from 2 inputs. So it's not 1 to 1. Question, is it on 2?
No.
No.
No. How do you know it's not on 2?
Because you don't have numbers in the image.
Yeah, we can't get negative 4 out of this function. Negative 4 is in the integers. We can't take the absolute value of a number and have it spit out negative 4. So there's another example with 1 to 1 and on 2. Good?
Good.
Another example. We're going to look at f is from, and I want to write out the sets explicitly to make you see it like that one way to make sure you realize it still makes sense. F is a function from the set 0, 1, 2, 3 to the set 0, 1, 2, 3. So here's our set A, here's our set B.
Domain image.
Domain, and the image is a subset of that.
Yeah.
Maybe it's the image, maybe it's not.
Right.
So far we just know F's image is a subset of that. Right? Back to over here. G is a function from A to B. What's the image of G?
6.
The set containing 6.
Oh, just put that. Okay, I see that. Yeah.
Click it now. Okay. So far we just know that the image is a subset of the set 0, 1, 2, 3. Maybe it's a whole set, but so far we just know that it's a subset. By now we write F explicitly. F is 0 goes to 1, 1 goes to 2, 2 goes to 3, 3 goes to 0.
Okay.
Question, is it 1 to 1?
Yes.
Yes, every output has a unique input. Is it on 2?
Yes.
Yes, the image is 0, 1, 2, 3, which is B.
So it's fine.
But it doesn't have to be the exact same.
What?
If you didn't have
It
a
doesn't have to
zero
be in
in
the same
there,
order.
it would still be
If I didn't have what?
a 0.
As the output?
You're saying right here? So replace that with a 1?
Yeah.
Then it is no longer on 2. And it's no longer 1 to 1.
Yeah.
Oh, that's right. I was thinking.
Stupid one.
Yeah.
Alright, good. More examples, the better.
Yeah.
So there's 1 to 1 and on 2. Now, it's often the case that we want to talk about the set 0, 1, 2, 3 up to some number. Right? And so we have a shorthand for that. When you see z sub n, that means all the numbers 0, 1, 2 up to m minus 1. Why m minus 1? Because it's the first m numbers. Notice that this was the first 4 whole numbers if you start at 0. So z sub 5 would be the numbers 0, 1, 2, 3, 4. It's the first 5 whole numbers.
Of that set, essentially.
And then z sub 4 would be 0, 1, 2, 3.
So you could.
You said of that set, I want to make it perfectly clear, this is only notation with z.
Okay.
If I replace that with r and put a 5 down there, meaningless notation.
Because you'd be starting from infinity. Or negative infinity.
However you rationalize it, it's fine. Meaningless notation. Okay. So, it's just writing that kind of annoying. Now I can just write that, which is a lot more convenient. Alright. So, next example. Now I'm going to write g as a function from z4 cross z4 to z4. So first I've got to cross these two sets with each other. This has 4 elements in it, this has 4 elements. So when I cross those two together, I'm going to have 16 elements. And then I need to take each one of those 16 elements and map them to something in here. So here's an example of g from z4 cross z4. Here's its domain. To z4, so its image is going to be a subset of this set. By, and now I wrote it all out. And there's 16. Notice all the elements of this set are going to be 0, 0, 0, 1, 0, 2, 0, 3, 1, 0, 1, 1, 1, 2, 1, 3, etc. So 0, 0 goes to 0, 0, 1 goes to 1, 0, 2 goes to 2, 0, 3 goes to 3, 1, 0 goes to 1, 1, 1 goes to 2, 1, 2 goes to 3, etc. And I mapped them all out.
Okay.
Now, this is not very consumable information for you.
No.
And even this way of reading this function isn't all that ideal in some cases. So we also have a notion of using a table to write out functions to help us consume it. So I'm going to rewrite this function first using a table. How do I do that? Typically you write some dummy variable, I chose n, and then f of your some dummy variable in the other column, and then you just fill out each column here. So 0 went to 1, 1 went to 2, 2 went to 3, 3 went to 4. So this is another way of rewriting out this function using a table.
3 went to 0.
3 went to 0, thank you. Now, let's write out this function in a more consumable way. I'm going to think about these are my 2 input things, and what they go to is the output. So what does 0, 0 go to? 0, 0 went to 0. What does 0, 1 go to? What does 0, 2 go to?
3.
Sometimes when I write 3s, I go to write the stupid brackets for sets. Breaks me.
1, 2, 3, 0, 0.
That's 0.
What?
Did I do it wrong?
Yeah, 0.
You said 2, 0 goes to 0.
But you also said 2, 2 goes to 0.
Oops. That should be 2 there.
Yeah, it should.
Okay.
And you can see the pattern.
Yeah, 2, 3, 0.
So 2, 1 goes to
3, 0.
3. This one was,
0.
is it a 0?
Yeah.
Okay.
1, 3, 0, 1, 2.
Okay. So notice how much more readable this is than that gigantic mess. And you can start to notice patterns. This was going 0, 1, 2, 3, and it counts up 1, 2, 3, 0, 2, 3, 0, 1, 3, 0, 1, 2. And you notice it's counting that way both rows and columns. Starting at a different number, just looping around once you reach 4.
So
Back to 0.
this is the case where someone decided z starts with 0, meaning it could have started with 1 and...
By definition, z sub whatever is 0, 1, 2, up to that number.
But you said that it depends on who's doing it.
No, that had nothing to do with the natural numbers. So this notation is well defined, and no one means anything different by this notation.
Okay, great.
Alright, so we can write tables for that. So now let's write another table really quick as our last example. And we'll call it the beats function. And we're going to do it for rock, paper, scissors. So we can think about a beats function for rock, paper, scissors. And we can think about rock, paper, scissors. Rock, paper, scissors. Sorry. That is not what I'm doing. I was going to do a different example. The beat relation. It's a relation. So we think about the beat relation now for a game of rock, paper, scissors.
Okay.
For a game of rock, paper, scissors, I'm going to use R for rock, P for paper, S for scissors.
Gotcha.
So let's think about the beats relation. Beats relation. Rock, paper, scissors. So if I do paper, what does paper beat?
Rock.
Rock. What does scissors beat?
Paper.
Paper. And what does rock beat?
Scissors.
Scissors. So this is how we can come up with the relation for the rock, paper, scissors game. And notice with relations, since I have P, comma, R is in beats, since that is one of the elements in that relation, it's valid for me to write paper beats, the name of the relation in the middle, rock. Good? Should we really quick cover equivalence relations, or are we overloaded on terminology? Let's leave it.
Just to clarify that the 2D grid there is an onto but not a one-to-one.
This is 1, 1, and on 2. It's a bijection.
Yeah.
Everything in this set was mapped to one and only one thing in this set, and everything in this set. Oh, sorry, yes. It is not 1 to 1. It's just on 2. I can't believe I said that. Obviously not a bijection. This has size 16. This has size 4.
Right.
Because the outputs are so.
Right.
Right.
We have repeating outputs all the time.
Yes,
Yeah, that was a weird moment.
but it is on 2.
It is on 2. It's definitely not 1 to 1. You cannot create a bijection between two sets unless they're the same size.
Right.
Wonderful. So yeah, we might even skip over equivalence relations. We won't do it for a long time, so.
Quick question on your Z sub M notation.
Uh-huh.
Is that only defined using the, how you define the integers? And then you just,
We use this notation when we want to do modular arithmetic.
right, so what I'm wondering is, how would you write it rigorously, if you were to give it a rigorous definition? So that is very precise.
For this,
Yeah,
well, once you already have the integers defined.
that's what I was wondering.
Oh, the integers are defined before this, yes. So they
Right.
define in terms of the
Right.
integers.
Okay. I'm just trying to pull back my memory.
Uh,
Are all those things defined in order?
Are all those things?
Here's what I mean. The integers have a natural sense of order, right? One thing comes before the next,
Uh-huh,
which comes before the next.
uh-huh.
But it's a set where order doesn't matter. So it's defined in order, but how do you use that notation and have a semblance of order?
You get order from your positivity axioms.
Oh, that's right.
Yeah.
See, these are things that I forget.
It honestly depends on how you come at it, because that's the real analysis way, where we start with the real numbers, and using the real numbers, we define the naturals, the rationals, the integers.
You start with natural numbers.
In real analysis, we start out with the real numbers are an undefined
They're
term.
undefined term, that's right.
Yep.
That's right.
Yes.
And then you define them using the other sets, right? Kind of.
And then you define all the other sets using the real numbers.
But you get a better idea of what they are using the other sets. Because you define the other sets using real numbers, then by the end you realize what real numbers actually are. Because it's like the union of the
The
other
real
sets.
numbers are the set satisfying the axioms on the real numbers.
Yeah.
That's what they are in real analysis. You can construct them from set theory,
Better intuition.
but
So you can define complex numbers by real numbers.
yes, you define the complex numbers with real numbers, and that definition is real easy.
In complex.
What's a complex number? C is equal to the set of all AB such that A and B are real numbers. It's just an ordered pair of real numbers. And we call that the imaginary part and that the real part. And we
Is
write
there-
a real number, or that the real part imaginary, and we write as A plus BI when we write it out. Well, it's just ordered pairs on the real numbers.
Is there
With-
an axiom that
We
you
need to
use?
find how you do addition and multiplication.
Is there an additional axiom for complex analysis?
No, just new definition.
For I?
For complex numbers, for how you do addition with complex numbers. But yeah, it's a natural extension.
Okay.
Anything else? Okay, wonderful. Yeah. Huh? You're set?
I'm set.
Yeah, so next time we'll do a little bit of graph theory and then proof by induction.
Are we doing equivalence relations?
I think we'll skip them. I can bring it up when it's natural. I was honestly just going to do a quick blast here, really quick saying what they were and some examples.